Cool. So we are live on YouTube and recording the meeting. We will have today Esteban Castro-Ruiz telling us about quantum reference frame related topic, more precisely about how can we jump to different perspectives of subsystems in what is called the extra particle approach. So Esteban, the stage is yours. Share the screen. Yeah.
Am I sharing now? Can you see my screen?
No.
No.
Okay. Can you see my screen now?
Yes.
Yeah.
Now yes.
Okay. Okay, let's go. Thank you very much, first of all, for the kind invitation to talk about our work here. And thank you, OFEC, for the organization. So I will talk mostly about work done together with Ognian Oreshkov some years ago. It's about, I might call it subsystems, extra particles, and all of these concepts. So maybe many of you were present in the quantum reference frame panel some days, weeks ago. So you can consider what I'm about to present here like a more technical complement, let's say, of our approach to reference frame transformations that I hope will help those of you who are interested to know about this framework more and would get interested in the framework itself, those of you who don't know it that well. So let me start by stating what is the problem that we want to solve. Suppose we have three systems, A, B, and S. And suppose two of these systems, A and B, are reference frames. In this case, they are flags. You can imagine them as reference frames for position, or more precisely, reference frame for the translation group. It's something that breaks the translation symmetry, thereby allowing you to define quantities that are, you could say, a priori not symmetric under translations, but you define them in a symmetric way by adding a reference frame. Suppose you have, relative to this reference frame A, that can be under control of an observer, call her Alice, the description of some system S and some system B, which is a reference frame from the description of some, or under the control of some other observer, if you wish, Bob. So Alice has the quantum state of all the things she can measure relative to her reference frame. And then the question is, if Bob, or more precisely, the reference frame of Bob, I will do this a lot. I will talk about Bob and the reference frame as if they were the same thing. They're obviously not the same thing. So, but yeah, as I'm used to that. So I warn you in case of, I say things that are not fully precise. This is a manner of speaking, let's say. If B is in a quantum superposition, how would, and I have relational data with respect to A, how do we find the relational data with respect to B? In other words, given the description of the system relative to A, of B relative to A, potentially something more, and this will be important, how do we find B with respect to A, the system with, sorry, A with respect to B, the system with respect to B, and potentially something more, okay? So it sounds a priori like a weird problem to be asking, because the reference frames that we're normally used to are, of course, not in quantum superposition. So I'm going to have to make some assumptions to attack the problem. And these are the assumptions that I'm going to make. First of all, I want to consider that even though I am looking at a system that has A, B, and S, or from the point of view of Alice, B with respect to her, S with respect to her, and possibly something more, there could be out there potentially some other external frames that I nevertheless am not describing. The second assumption I want to make is, well, one is kind of almost the definition of lacking a reference frame. If you lack a reference frame for a certain group G, you can only measure or have access to operators that are invariant under the action of such a group G. Moreover, you can ask, how come then we can apparently in the lab where we believe that we have this kind of potentially not access to external frames that are outside the lab, measure things that are nevertheless invariant in principle? The answer comes with these observables, which are called rest observables or YEND observables, are called like this in this paper, which are somehow the observables that you could understand them like if there were some external observer looking at Alice measuring S. Alice says, I measure S. How would this observer describe such a measurement? Let's say, have he access to, like, let's say, an external reference frame and access to and control to Alice's own reference frame? And then the assumption is that these observables or this question is answered by means of these YEND observables or these G-twirled observables. As an example, very kind of basic one, if you put here X, which is something that is in principle not invariant under translations, this will give you XS minus XA. So it will turn a position operator into a relative position operator. Okay? So with these two assumptions, what can we do? We start from Alice. And then she can reason like this. She can say, oh, potentially there could be another reference frame out there with respect to which I'm going to use the normal rules of quantum theory. Let's see how he would define the problem. So he has access, or she, let's call her Eve, access to an external frame that Alice, Bob don't have. And she can look at the situation somehow from above. In the end, this Eve will be something like a theoretical scaffolding, so to speak. In the end, we will get rid of it. So Eve says that Alice is measuring X, and then she represents this as a relative or dressed observable because the fact that Alice doesn't have access to the external Eve's frame means that she can only measure invariant observables. This is an invariant observable. And in particular, we assume that she can measure these ones. These ones are important because in the limit where the reference frame is very sharp, namely when the inner product between these G states that somehow tell me how my reference frame is oriented, in that limit, I recover some isomorphism between the system as defined relative to the external frame and the system as defined relative to Alice. So you could take the view that we always measure this kind of observables, so to speak. But nevertheless, we talk about, we neglect the reference frame because we have very good frames and we have systems that through these observables are isomorphic to the kind of ordinary orthodox quantum mechanics observables that we're used to talk about. Okay, we said we have access only to invariant observables, but what are all the observables that we have access? We haven't talked about this. So imagine for a moment that we grant access to the invariant observable E, sorry, to the external reference frame E. From the point of view of somebody who has a description of this reference frame E, what Eve does is she measures relative observables with respect to her reference frame that look exactly like this. In particular, everything she can measure from the system A, B, and S has this form. She measures everything relative to her reference frame for group G. Okay? And then imagine we lose E. We wipe it out from this equation. we apply some depolarizing map. I don't know exactly what is the formalization of it, but we apply some, yeah, we wipe it out. And what happens in the end? What are we left with? What we're left with is, of course, the integral over G of what we had before after we wipe out the reference frame, namely the invariant subsystem, the set of all operators that are invariant under the action of G. Okay, so this is an argument to say all operators which are invariant are also accessible. You can imagine having the reference frame and then losing it, and then this leads immediately to these operators as the ones that remain. Now there comes a subtle point. You could say, okay, yes, but these invariant operators assumed some sort of dependence on the external reference frame Eve. What happens if I have another Eve prime? Would she also define the invariant observables as the relevant ones? It turns out, yes. The answer is yes. In a technical sense, the invariant operators of A, B, and S is the largest subalgebra that is common to E and E prime. So if E prime were to state the same kind of problem, she would arrive to exactly the same object, the same invariant subalgebra of A, B, and S as the relevant object that you should look at when you lack access to this reference frame. Okay, so now let's go into this was somehow like the context, let's say. Now let's look at more precisely how we solve the problem. Okay, so
Esteban,
yes.
can I ask a question, or do you want to only
No,
have
please,
questions at
please
the
ask.
end?
Yes.
So about this context, just to make sure I understood, you will use A and B, and you will
Yes.
move between the frames of A and B, and E and E prime, you introduce them. You said they are a theoretical scaffolding
Right.
because you want invariant observables on A, B, and S.
Correct. Yeah.
Okay.
This is like a conclusion of what the way I state the problem is I want to from A go to B. I want to
Mhm.
find out what B sees, given what A sees.
Yeah.
How do I state the problem and how do I solve the problem? And then the way I state the problem is just in a very conservative way. I say there could be some reference frame outside. If there were, how would this reference frame outside see what's going on? And then I use this reference frame. I use the structure of,
Mhm.
according to the reference frame, what is going on. And then I'm going to derive the transformation by means of this theoretical scaffolding. What I said in the very end is something like you could ask, what if I have another potential external reference
Mhm.
frame? Well, it doesn't matter. This is because the relevant
Mhm.
object is the invariant subsystem.
Okay. Okay. Thank you for the clarification. Yes, I might have another question, but this is more for the end. Okay. Thank you.
Okay. Are there any other questions at this point? No? Okay. Okay. So now I will get a little bit more technical. We made the assumption
I
basically.
have a quick question. Sorry.
Yes, please.
What do you do if your symmetry group is non-compact, like the group of translations
Yes,
in
there
the
are some technicalities that you have to take care of,
Mhm,
like this G twirl of operators is a
mhm,
priori not well defined because normally you have to divide by the
mhm,
size of the group, the volume of the group. But I think you can take care of these.
mhm.
Yes.
Okay. Okay.
Okay. Yes, if you want to be, let's say, absolutely rigorous and have an absolutely rigorous picture in mind, consider this is a compact group. I believe it can be extended to non-compact as well. Like my main point is how you state the problem on the conceptual level. Let's say this is what I want to transmit now.
Yeah, no, sure. That sounds good. Yeah.
Okay. So
hello, excuse me, I have a question. When you say that you change from reference frame to another, actually, you mean like a class of reference frame that share G as, let's say, some kind of fundamental group, right? Or it could be any E and E prime.
I'm not completely sure I understand the question. Maybe let me try to answer as follows. I have Alice. She has a reference frame for a certain group. She measures stuff relative to this reference frame for a certain group. And she sees that Bob is in a superposition, or his reference frame is in a superposition with respect to this group. What is the information that is necessary for her to describe what would be the state according to Bob? I think this is the question. So there's no fundamentality here in any like kind of strong sense. It's just you have no access to the external frame.
But if I understood well, so she pictures like there's an external reference frame, Eve,
right,
with which she shares the same kind of group invariance. I mean, A and E share a common have a common dictionary, which is this group G, right?
Yes, I guess you can say something like this. Yeah, I would just say she pictures some E that has a reference frame for group G.
Which is her same group. It's
her
not
same
like,
group. Her same
it's
group.
not
Yes.
like
Yes.
V kind reference frame.
Correct.
The existence of the representations is probably this dictionary.
Probably, yes.
And E prime is again of the same kind.
Of the same kind, yeah. Whenever I say external reference frame, I mean reference frame for group G. And whenever I say reference frame here, I'm talking about reference frame for group G. This is actually very important. I'm not talking about everything else that is not symmetry with respect to G. I am assuming is given. I'm just talking about the lack of access for a reference frame or to a reference frame for group G. This is, yeah.
Okay, and at this point, you're not supposing anything. If I have, let's say, an E and E tilde, which have different Gs, right? They cannot talk, right?
In the end, they will be removed. They're not very important. This is just motivation for how we derive the transformation. Maybe let's continue. Let's go to questions maybe at the end. Okay, so how does the subsystem structure of this A, B, and S look like with respect to this potential external observer E? So I'm gonna describe more in detail A, because it's the frame where I eventually want to start from and that I want to use to jump to B. So the reference frame A, I am assuming that it is a perfect reference frame. In technical words, it carries the regular representation of the group G. And then this is why I wrote it like with a direct sum over Q's. Q's are the irreducible representations of the group G. So the group will act on, let's say, roughly speaking, the center of mass subsystem, and there will be also some multiplicity subsystems that are invariant under the action of the group. And then I will have, of course, the part that corresponds to B and S. In particular, B will also be such regular representation. From the point of view of E, the group acts both on the center of mass, that by definition I define it to be the left part, and it acts with some unitary representation on the system SB. This is just the setup by definition, let's say. Then how do these observables that I was talking about, that are the ones that when Alice says I measure S or T or whatever operator, E describes from her perspective. if you see, they have support, or they're non-trivial in all three parts of this subsystem decomposition that I have. What I would like now is to go to some description that looks more like ordinary quantum theory, where a subsystem is simply a tensor factor of the Hilbert space, something that looks more like Nielsen and Chuang, in such a way that, in a sense, the reference frame becomes implicit. I am using it, but I'm using it in the background somehow. And this would be Alice's description. So how do we do this? First, we have to notice that there is something else that we have to pay attention to, namely some other set of invariant operators which are not of this form of operators relative to reference frame A. More technically, they are the commutant within the invariant subalgebra of these guys. You can take this formula and then put an arbitrary observable here, and then compute the commutator with some observable here, where this is invariant under translations that act only here, so it has support only here, okay? And you will see that this commutator is 0. Moreover, you will see also that these operators are invariant, okay? So this is a subsystem. It's an invariant subsystem, and it complements the relative observables, or the relative subsystem, to form the full invariant subalgebra of operators in the Hilbert space of E. Now, it turns out there is some refactorization of the Hilbert space. The details are in this formula here, in this unitary, such that we can look at an isomorphic Hilbert space where the world, so to speak, is partitioned in a different way, okay? And this will be called the perspective of Alice. All the things that are dependent on the reference frame E, to which Alice has no access to, will be mapped to this left part of the regular representation. This is gauge for Alice. Now, the systems B and S relative to Alice will occupy a separate tensor factor, just like in ordinary quantum mechanics. This is what we wanted to do. A separate tensor factor here, okay? But then we have to pay attention to this other piece of the Hilbert space. It turns out that this S relative to A bar that I described before is actually mapped to this right regular representation in this Hilbert space. And then the full invariant sum algebra is not this one, but this full thing. And this, once we jump at Alice's frame and we look at this subsystem, this is what we call the extra particle. So we want to argue that if you want to consider the possibility in the most general terms of having reference frames in superposition and so on, to define how to jump between them, etc., you have to append this system and have it always by your side and consider it whenever you want to do this. This is not something we normally discuss. These are degrees of freedom that are there and so on, but we don't take them so much into account. You can ask, why not? The reason is that, or some explanation can be that if your reference frame is classical, namely in one of these states G, which is, we could say, a very good reference frames like the one we usually have in the laboratory, then the state associated to this subsystem turns out that it factors out, so it's not correlated to the relative subsystem, and it's also proportional to the identity, so in a sense carries no information. So if our state is in one of these very sharp reference frames, you can just ignore it. Okay. Of course, we want to consider the situations where we are in a superposition of the G's, and then we're not going to ignore it, and this is part of the point of my talk. So the important takeaway, let's say, technical takeaway, is that the relative observables are not the full invariant subsystem. Our invariants are contained, but don't exhaust it. Now that we have separated the subsystems, the relevant subsystems, we can just forget the external potential reference frame by saying, oh, I start from Alice's description, then I move to this potential external observer, and then I move to Bob. And then I find a transformation that goes directly from Alice to Bob. And then if I want to check if this transformation is correct, I just have to ask Bob, did I predict your state correctly? Did I predict your probabilities correctly? So this is something that Alice can fully internally check with Bob. And now, something that is important to derive this transformation is just what I said, is that the full set of invariant operators is actually the union of these extra particle degrees of freedom and these relative subsystems with respect to A. So why is this important? Now Bob will describe, we will arrive at the composition in which Bob will describe A and S relative to him. And then we can ask, if we want some information about this subalgebra AS relative to B, from the point of view of Alice, where do we look for this information? So the idea is something like Alice and Bob have two different ways of partitioning the world, so to speak. And then moving from Alice to Bob is moving between these two different ways of dividing the world into subsystems. What is the relevant information? Well, let's look at this diagram. For instance, if Bob wants to see, if Alice wants to know how Bob would describe her reference frame, we have to look at this diagram and see with what subsystems defined with respect to Alice it intersects. Well, it intersects, of course, with B relative to A, makes a lot of sense. It intersects, of course, with S relative to A. In the end, A's reference frame is involved in measuring S. But importantly, this is not the full information. It also intersects and by intersect, I mean don't commute. This is what this, so that observables here have information about this subsystem here. So if you want to gather the full information about this subsystem from the perspective of Alice, it's not enough that you look at this subsystem and this subsystem. You also have to look at this subsystem, okay? So let me give you a more concrete example of this. This is recent work with Thomas Galli and Leon Loveridge. We set out as a group set 2, so as to make it very simple, and assume some external observer who had two states, two pure states, psi1 and psi2, such that when moving to the reference frame of Alice and looking at the state of B and S relative to her reference frame, the state is the same no matter whether we start with psi1 or psi2. But when we play the same game but jump to B instead of A, it turns out that it does matter whether we start out with psi1 or psi2. In fact, you get two orthogonal states relative to Bob if you start with this or that. And then you might ask, why is this so? And then the answer is that there is extra information that you would need in order to find out what is the full state. And this extra information precisely lies in here. So I'm just giving you an example of a concrete instance in which this extra particle captures this information. Okay, now let me just say one last thing to exemplify, or something that is weird and people like to talk about, and I think it's fun to think about, which is called the paradox of the third particle. I think it will illustrate a little bit the nature of these extra particle degrees of freedom, why they are interesting, and what they tell us. So there's been many presentations of this paradox of the extra particle. The original one, as far as I know, is a paper by Angelo and collaborators. Now I'm going to present a different version of the paradox of the extra particle, which is somehow targeted to our formalism. So the idea is as follows. So start with the same setup. Say you are in A, and you want to jump to B. And say B is in a superposition, and you have S in some kind of more or less well-defined state here. Then you could reason as follows. You could say, oh, for each amplitude of B, I will jump as if it were classical, and then I will just superpose all of the amplitudes. Then this means that for each amplitude, I will have a different translation of A and S, leading to the idea that once I go to B, A and S will be entangled. Okay, this sounds reasonable. And the important thing to note is they will be entangled, yes, but they will be in a pure state if the state you started with in the first place was pure. Now let's rerun the argument again, but insert a different system S tilde. By the same token, when I move to Bob, I will go to a system in which I have three-partite entanglement, A, S, and S tilde. So now I will trace out S tilde, and I will obtain a mixed state. So how is this possible? I'm not saying this is a paradox of the form like 0 equals 1 and so on. And there are many ways out of this paradox, actually. You can say, okay, I'm very practical and I include S, S tilde, S double tilde, S triple tilde, and so on until I form a closed system. I'm completely sure there's nothing else there relevant. And then I do my transformation and I'm happy. This is certainly a solution. What I'm saying is something that might be leave us a little bit uncomfortable with the nature of the frameworks. Like it would be nice if there could be a description in which all the information that you need to jump to Bob and see how Bob sees A and S is given in how Alice sees Bob, how Alice sees S, and potentially something else. And then the answer is that this potentially something else is the extra particle, and then it turns out that this extra particle contains, in a sense, all the possible S prime. It has information about all the potential S tilde, S double tilde, S triple tilde that might be out there, so to speak. So the way one can look at this is one can say there are restrictions, of course. There are restrictions. If you look at the extra particle in particular, the only case in which you can assume that there is an S tilde in an arbitrary state is if the extra particle factorizes out to the identity, namely if the description of Alice is compatible with being in a classical state with respect to some potential external observer. It's interesting to ask, and we're working on this with Bruna Sado, my student. Okay, given other states of this extra particle, what are they compatible with? What can be out there? It turns out that if you sort of put this extra particle into the game and consider it as an extra subsystem, then no matter whether you have S or S prime or S tilde, sorry, S double tilde. Here I'm putting the equations. I don't think I need this. I better explain. No matter what else is out there, whenever you trace whatever else you have out there so that you look only at S relative to A and B relative to A, in particular, you have to trace this extra particle degrees of freedom, you obtain exactly the same state, okay? And then this is a way in which you can address this problem. And then there is a sense, therefore, in which if you want to know only what would be the state of of A and S relative to B, you need the minimal information that you need if you start from Alice is the state of B and S relative to A and the extra particle. A little bit more technical, a sense in which these degrees of freedom tell me about something that is out there can be understood as follows. So if one looks from the external perspective, okay, there's a typo here, but I'm missing one integral over h, and then this is just the. No, sorry, I'm not missing one integral over h. You have to delete this. These are the relative observables. Yes, very good, thank you. These are the relative observables of S tilde with respect to A, okay? They're non-trivial here, reference frame of Alice, and they're not trivial in S tilde with respect to this external, potential external observable. They are trivial nevertheless here. Now let's look at the extra particle, but just without the S tilde, the extra particle of B and S with respect to A. This is a well-defined subsystem that can be embedded in the kind of subsystem that has this S tilde as an extra system that we added. This now goes, now this is correct. One need not, this equation is now correct. It acts like identity here. And then the important point is that these two subsystems don't commute. Any other potential subsystem that I might want to add as a relative subsystem with respect to A will not commute with the extra particle defined with respect to the subsystems that I already had. This is a bit weird, but it's like I wanted to go a little bit more into the technical details, and this is, I think, what is at the core of this apparently paradoxical situations. So with this, I hope I managed to transmit the main features of this work, and I thank you for your attention.
Thank you, Esteban. Thank you. It was very insightful. Also, had some rigor to it. I liked it.
Yeah, I mean non-compact and so on, but I mean, yeah.
No, I did not mean this. No, I liked this theoretical scaffolding with the eaves from the outside. Does anyone have a question? Can use the raise hand feature of Zoom. No questions?
Come on, don't be shy.
Don't be shy. Max Josefan, please.
Hi.
Hi.
Thanks a lot for this very nice talk. I would have just a probably very naive question out of curiosity. You said right very much in the beginning that you can bind this transition, so to say, from quantum to classical reference frames by yes, by only being in, for instance, one state of this G. And is there some mixed, some intermediate regime where you would say, okay, you actually have almost classical-like reference frames, but still some specific quantum effects that pop up in this description? Would there be something which you could identify and say, okay, this would be maybe some first hint in this direction with some first layer of effect, some kind of, I don't know if this makes sense, this term.
It makes a lot of sense, and I think it's important, yes. I think something I didn't say is that these states G actually don't exist, right? They are idealizations. I mean, I don't want to say they don't exist, but they are kind of, if you want to be mathematically rigorous, they are normalized up to a delta function for like continuous groups. What does exist is like a physical approximation where you can talk about your reference frame effectively by saying this is perfect, and this is what we effectively have in the lab. You can construct states such that by adding more resources, so to speak, approximate these states. And then if you play the same game with these other states, you can find extra features, as you say, that deviate a little bit from the, let's say, ideal case.
Okay, thanks a lot.
Samuel, please.
Great. Thanks a lot for the talk. I was wondering about the difference that you emphasize on between the framed observables and the invariant observables. And I was wondering whether there was any property of the quantum reference frame that made these equal to each other. For example, if the frame observable maybe is informationally complete or something like that, do you expect these to be equal? And if so, do you expect this approach to be equivalent to the operational QRF approach, or how do you see these?
I don't know, honestly. So there probably one will have to be kind of careful about which algebras we're talking about and so on and so forth. My intuition is that no. My intuition is that these. So what is the safest I can say? If your group is compact, for example, and you define these observables, then these observables don't exhaust the set of relative observables. This is kind of, I think, fair to say. And then you have to look at these others if you want to kind of solve the jumping problem in full generality. I don't know if there can be other cases, honestly, more special where you can see that actually the full invariant subsystem is but this is not to say, I think this operational approach is completely compatible with our approach. Completely. It just depends on what kind of assumptions you are using. If you want to focus on them, then I think one will have to check, of course, but at least for simple cases, you will get the same answers if you focused on the end observables.
Can I ask for clarification of the question? Just about what do you call the frame observables versus the invariant observables? Is the frame observables the relative ones?
Yeah, I think he.
Is that what you
So
mean?
the image of the Yen map, yeah.
Okay. Just
Yes.
Thank you.
Thanks.
I have a question regarding the example from your work with Thomas Galli and Leon Loveridge.
Right.
Um,
Do I go back? Am I?
You can share
sorry.
it again if you want.
Maybe I was too quick on share.
So there were two states, psi1 and psi2. Maybe I missed. Did you say something about them? You said that Eve sees two total states, psi1 of psi.
Yes.
psi2.
Yes. Just a second.
Mm-hmm.
I said that Eve sees two total states. Yes. Where was this? Okay. Yeah, so the idea is the following. Eve has, like the whole example is much more concrete than this. I didn't want to go into the full details of it because I think I didn't have time. But the idea is the following. We have two states. And then the important thing is that these two states have different total charge. In the end, this extra particle is very much related to the total charge. If the group is translations, then this extra particle is basically the total momentum. Okay? You have two different states with different total momentum with respect to Eve. And then you want to know how the state of B and S looks with respect to Alice. And then what you find is that the state is the same, no matter whether you start with psi1 or psi2. This is the idea. This is just like a fact by construction. Like Thomas found two states that satisfied this. Okay.
These are two specific states or for any states?
Two very specific states. Yes. Yes, exactly. Maybe this was the, yeah.
Okay.
And then these are very specific such that when you jump to B, it does matter whether you start out with psi1 or psi2. In fact, you get two different states, two orthogonal states, depending on whether you start with psi1 or psi2. And then you can ask, there is clearly here not enough information for you to know what is the state here, you can ask, where is the extra information? And then the answer is the extra information is here.
You're not sharing the screen. Here, you mean with
I'm
me?
not sharing the screen.
Yeah.
Oh, okay. I thought I was. Okay, sorry.
So the extra information is with B. Or
Yes. Okay, good. Sorry.
Mhm.
These two are equal. So in this subsystem, there is not enough information to find out what
Mhm.
these states are. You can ask, where is the extra information? The extra information is here.
Mhm.
It's invariant. So it's something that, by the argument I presented above, is a priori accessible, but is not of the form relative observable. It is this
Mhm.
extra particle degree of freedom.
And the two orthogonal states of AS from the perspective of B,
Right.
will they be orthogonal because they have two different eigenvalues for the charge operator on AS relative to
Oh,
B,
this is a very good question, actually, Osaka.
or because
I
of the
don't
position,
remember.
or something else? Okay.
If I remember correctly, I don't know if Thomas is there. They differ they're subtly different. Like, I think if you go on the basis that is of like states that are asymmetric with respect to the action of the group, I think both of them will give you the same probability distribution, but it is in the phase. They have a different phase.
So the charge. So they will have different charge eigenvalues.
So that the charge will induce a different phase, so to speak, so that there are observables on this relative subsystem with respect to B that can distinguish them.
Okay. Okay. This is a paper that exists already?
Yes, this is
Okay.
it was out this year. Yeah.
Okay. Okay. Thank you, Esteban. Are there any more questions? Okay, doesn't seem like it. So let us thank Esteban again with the React button.
Thank you.
And thank you all for attending the KISS seminars in 2025. Have all happy Hanukkah and Merry Christmas. And see you in the WAS seminars.
See you.
Bye-bye.
Bye.
Bye-bye.